the super exchange interaction, if the angle is more, then the interaction is more, right?
Yeah, if the angle is 180 degree, that's the most ideal.
So I did not understand.
So if you know, for example, these two ions are here and oxygen is in between, and they are on a straight line, at that time there is a maximum interaction.
So it is.
But suppose you know this bond is like this, another bond is like this. So it depends on the angle. Smaller is the angle. For example, if you have one like this, then exchange interaction will be very low. So basically, the angle between two bonds, the larger it is, I mean larger means up to 180 degree. Okay, maximum. Then it will be maximum. Okay. So it depends on that as well as the distance. If the bonds are too long, then again the exchange interaction will fall off. Okay. So both the things play a role. So what happens in the case of spinels, as we can see, the angle is 120 degrees or whatever I calculated, I don't remember. The slides will be there. So I have prepared the slides for circulation, but because of Wi-Fi I could not do it. Lecture 1 I have already done. So it's the largest amongst the three interactions, because there are three interactions possible: AA, AB, and BB. So AB is the largest because the angle is largest and the distance is also small. Okay, BB angle is 90 degrees, which is not very good, and therefore this is a weaker interaction. And if you are taking AA, that's still smaller, 80 degrees, and the distance is also very large because you know the A atoms are very far apart from each other. So it goes like that. So the AA turns out to be the weakest out of the thing. In general, all the three interactions are antiferromagnetic, but AB dominates. When AB dominates, then all the ions on A, though amongst themselves they should have acted antiferromagnetically, but because of the strong coupling between A and B, they all become parallel. And B become parallel. That's what is the Nails model. That magnetic moments in the B side, you all add them, and all the magnetic moments in the A side, you add them, and take the negative of the two, about which I will talk today.
Thank
you. Any other questions, comments? Yeah, if you have a question, raise your hand, because for recording purposes, this is needed. That's why we want it put through the mic. So
we can start? Okay. So in yesterday's class, we discussed one of the important parameter which affects the shape of the mesh loop, and that's the anisotropy. There is another criterion which is magnetostatic energy criterion. Of course, as we have said, that the loop at any given field or the value of magnetization at any given field will depend on the energy minimum of the magnetic domains. The magnetostatic field interaction is already accounted in the shape anisotropy, so that's what I am not going to discuss. But there is another role which I will discuss a little bit, is about domain walls, which we call exchange energy. What happens, as we know the exchange, let's talk of a simple ferromagnetic system. If you are talking of exchange, it tries, and a ferromagnetic exchange, it tries to bring all the magnetic moments parallel to each other, in the layman's language. All right? Now, if you are having magnetic domains, let's say there is one particular magnetic moment which is aligned in this particular direction, in which all the magnetic moments are aligned in this particular direction. And neighboring to that, there is another region in which magnetic moments are aligned in the opposite direction. Let's just take an example. That's why it's magnetic domain. If it would have been aligned in the same direction, this would have been only a single domain. All right? It means these two magnetic moments have to differ in the direction. In the case of easiness, I have taken them to be anti-parallel to each other. All right? Now, what happens when I go from this domain to this domain? There is a domain wall in between. All right? Now, in principle, it's not possible, in general, that magnetic moment just before the wall is like this, and just after the wall it becomes large, because the angle between them becomes too large. Okay? It means it has to work against exchange, because exchange is trying to pull them together, and in order to create a domain wall, you have to create an angle between them. Okay? It's like that, if you have two balls, which you are trying to align, which you always like to remain like this, and you want to pull them apart, okay, you have to work against that spring, which will try to make them bring them together. So exchange is trying to make all these magnetic moments parallel to each other, and you are creating a wall if I am going from this particular domain to this particular domain. So you have to work against the energy. You have to again work against the exchange forces. So generally this particular wall, which is a transition between one domain to another domain, is not instantaneous in general. Instantaneous means not time-wise, but position-wise. It doesn't happen just over one lattice constant that you are having here, and suddenly it becomes here. Of course, there have been cases in which it has been found like that, but they are very, very special cases. In general, this transition will take place over multiple lattice constants. Slowly, the magnetic moment will change from one direction to another direction. This is what we call as a domain wall. Now, domain walls can be of various types, depending upon how the magnetic moment makes a transition from this particular domain to this particular domain. Let me give an example here. Let us suppose my magnetic domain here in this particular direction is pointing like this. All right? And let's assume that this table is a wall. All right? And now the second domain starts where magnetic moment is now like this. Is it clear? That in this direction the magnetic moment is like that, and this is the transition region where magnetic moment is making a transition from this particular direction to this particular direction. As I mentioned, it has to happen over a certain amount of distance. It cannot happen instantaneously. Now there are various ways in which it's possible. For example, as I am going like this, as I keep on moving, the magnetic moment keeps on going like this. And then makes a transition like this. Understand? It means I am going like this from here, slowly going up across the wall like this. It means magnetic moment is always pointing out in the direction perpendicular to the wall. Another possibility is that if I am going from here to here, I make transitions like this. All right? It means my magnetic moments are lying along the wall. There is nothing special about these two directions. It can happen like this. Okay? There are various possibilities in which transitions can take place from this particular domain to this particular domain. And depending upon how the transition takes place, the wall energy becomes different. All right? Now we take two special cases. One what we call as a block wall, which is generally most common. In block wall, you make transition like this. All right? And nail wall is the one in which you make transition like this. This is what is called nail wall. So this is one wall which is called block wall. And in between there could be separation between block wall and nail wall. In fact, we will talk a little bit in one of my later lectures about magnetic bubbles. The magnetic bubbles have lost their glory. They are no longer being used, and a large number of today's magnetism people probably would not even have heard about magnetic bubbles. But I always like to narrate that story because it's a very beautiful story, a tragic story. All right? Mainly because it led to a lot of very, very interesting physics, both from the point of view of technology and both from the point of view of understanding physics. So I always like to narrate many of these type of walls were seen in magnetic bubbles. In fact, understanding of domain wall happened much better after magnetic bubbles came. Earlier, if you read the textbook, they will define block wall, nail wall, but how these transitions take place and all those things, they were not very clearly defined. So this particular understanding of the domain wall phenomenon was considered more in the time of magnetic bubbles. All right? So we understand that as we create a domain wall, I have to spend certain amount of energy. And generally, if you have to minimize exchange energy, then bigger the wall, minimum least will be the energy. Now you can understand one of the important things is that if I am having a very, very tiny particle or a tiny grain, it means a material is polycrystalline, but one of the grain which is single crystal, because a polycrystal consists of a large number of tiny single crystals. If its size is very, very small, then if I have to create a domain wall within that, it has to be still smaller than the size of this particle. Okay, if this is my particle, and if I have to create a domain wall has to be somewhere in between the particle. So the size of the domain wall still has to be smaller. So there will be a time when it will be not possible for this particular particle to have any domain wall. It will always be single domain. Okay, these sizes can be calculated depending on various other energies. But again, I would like to remind you of our classical days of tape recorders, where we had particulate media, as we used to call it. That's the type of particles that they were using at that particular time, when the entire particle was a single domain. All right? So this is one of the energy. Now let's talk about various type of shapes, how these particular energies will be affecting. The mesh loop. Let us start with exchange energy. As we said that if we have to minimize exchange energy, ideally the material should be single domain. Then the exchange energy will be minimum. It would not like to create any domain wall, because exchange, you have to work against exchange to create a wall. All right? So the minimum of exchange energy will take place only when there is no wall. All of them are parallel. So suppose we have a material like this, and this material is, let's suppose, a single domain. This is what would happen if exchange energy is the most dominant energy. But in this case, you are creating poles, and this will create a large amount of magnetostatic energy. So magnetostatic energy would like that rather than this, you would have another domain like this. Now it's a gameplay between the magnetostatic energy and the exchange energy, how many such type of walls it can support. And that will decide what will be the domain structure. In fact, what you normally see is what we call as the closure domains, which minimizes again the magnetostatic energy, and you don't have domains like this, but you have domains something like this, which we call as a closure domain, and this angle is 45 degree. These type of domains are generally beautifully seen only in single crystalline materials. In polycrystalline materials, there are so many other complications that you know. Okay, so this will sort of minimize the magnetostatic energy. But what about anisotropy? It's possible that this is an easy access, but this may not be an easy access. So if a domain has to align itself in this particular direction, a magnetic moment has to be aligned in this particular direction, anisotropy energy will play a role. In fact, if anisotropy energy is the dominant energy, you will find all the domains to be aligned only in this direction. Why would they go to a difficult direction, hard direction, if there is no other energy? But I said you have to have interplay between different energies, and that's what's going to decide your domain structure. And when you apply a field, then all these energies will get affected, and therefore a new domain structure will form, and that's how the mesh loop will be formed. That's what will decide what is going to be the mesh loop. Now let us suppose of a case where anisotropy is dominant. Let's suppose it's a uniaxial anisotropy, which is generally seen in the hexagonal structures. Okay. For example, cobalt shows a very large uniaxial anisotropy in the C direction. All right. In that case, what happens if you have magnetized, initially let's suppose we have a demagnetized state and we want to magnetize a sample, and you are trying to magnetize it along one of the easy direction, let's suppose the C axis, which is the easy direction. You have magnetized and it has reached to a saturation. It means now all the material, entire material is a single domain material. Either the favorable domains have increased their size, or other domains which are in a different direction have rotated themselves and aligned themselves with the merged them with the same domain. Eventually in the saturation you have only a single domain. All right. Now this is an easy direction. So these all domains have found their favorable position. Position means position under quotes, which I essentially mean that this is where they would like to be. It's that direction where they like to sit. Now if I try to reduce the magnetic field, there is no reason why they should move. All right. Now if I keep on reducing the magnetic field, all the domains will peacefully be in the same direction. Remanence will be 1. Mr upon ms will be 1. If that is the only energy which is taking important role, okay, there are many other energies also. All right, but I am taking an example of a material where uniaxial anisotropy is a dominant anisotropy, and such materials are very, very important and have been made, especially during the time of magnetic bubbles and even later for recording. You want what we call as a square type of loop. Now you try to apply magnetic field in the negative direction. Magnetization will still remain in the same direction until you have applied enough field. See, the problem is that if magnetic moments have to align themselves in a direction different from that, or want to go from one easy direction to another easy direction which is opposite to it, I am assuming a uniaxial crystal, then they have to always move through a hard direction. It's like a potential well. They have to always move through a hard direction. Unless you are supplying them enough amount of energy so that they can cross over that particular hard axis energy required, they will not move. They will remain in the same direction. And once you have provided them, they'll flip over and go to the other direction. This is what is called a square loop. And as we had discussed yesterday, these are the type of loop ideally required for example, recording material, which writes clearly one bit. This region is completely magnetized, then this region is magnetized in a different direction. Okay, you don't want any transitions in between them as far as possible. But yesterday I was telling this story with someone when one of my colleagues was working with our collaborator in France for one of the lab, when the person thought that something wrong has happened with VSM, he's getting always the same signal. He's changing the field but nothing is happening. And then he applied suddenly a large field in reverse direction and tuck, it went to the other direction and again remained constant. So either remains, it's just like a binary state, either remains in this direction of magnetization or other direction of magnetization, because the uniaxial anisotropy is so strong. So what we have seen that how these various energies can shape your mesh loop, and what we had discussed last time, that one of the key factor of utility of a magnetic material is its mesh loop. Okay, of course, there are many other parameters also. I even admitted that's an overstatement saying that all that you require is to tailor MH2 because temperature dependence, Curie temperature, the temperature at which the magnetism gets lost. There are many such things which are also important for the utility of a material. But as a material scientist, I think most of us who are working not really in industry but working as an experimentalist researcher are essentially looking at the shape of the MH2. That's what is our bread and butter. All right. Now, there are very, very few materials in which you really require for utility purposes single crystalline material. First of all, single crystal material is difficult to grow. It's expensive to grow, let me put it like that. Not only difficult, it's expensive to grow. Probably, if I remember, during my tenure as a researcher, magnetic bubbles were the only cases where you really used a material in the single crystalline form. And probably that was one of the reasons of their fall, because it was very expensive to create at a bulk rate that high quality film. Most of the time that we use materials, they are polycrystalline. And when you have polycrystalline materials, they are not intrinsic but extrinsic factors which also play an important role and play much more important role. Therefore, there is something which we call as a texture and orientation, about which I will just say a few words, which becomes extremely important for the utility of a magnetic material in polycrystalline form. Both the words texture and orientation mean nearly the same thing, but one of the words is stronger than the other. Let me explain what I mean. As you know, a polycrystalline material consists of a large number of single crystals, which in common parlance, common language, we call them grains. Okay, it's a combination of very, very large number of tiny single crystals. Now, I will call this material to be completely untextured if all these grains amongst themselves are randomly oriented with respect to each other. Remember this, I am not talking about magnetic domains here. Magnetic domain is a different question. All right, magnetic domains will depend on those type of energy. Here it depends on how you have made the material. Okay, which type of method you have used to prepare the material. This grain structure, what we call, is embedded, is fixed. Of course, you can change it by again thermal treatment and things like that. That's a different question. But in general, if you have prepared a material, your grain structure, grain sizes as we call it, they remain fixed. They are not going to be affected by magnetic field or things like that. But if you find that all these grains are oriented randomly with respect to each other, then we call that this material is untextured. There is no texture in this. And many times we want a texture. It means we want some preferential alignment of grains. And orientation is a little more stronger terms. For example, let us suppose this is the, let's talk of thin film. I'm a thin film person, so I think more in terms of thin film. Let us suppose this is table is a thin film. All right, here it contains large number of grains. Okay, there is one single crystal here, there is one single crystal here, there is one single crystal here. There are so many single crystals here. And let us suppose it's a cubic material, and this particular material is oriented in 111 direction. What it would mean that for all the grains, the 111 direction will be like this. One of the 111 directions. See, 111, there are 8 equivalent 111 directions. 1, 2, 3, 4, 4 below. 111 and equivalent directions. All right. Now, they are aligned in such a fashion that one of the equivalent 111 direction is like this. Other direction could be random in the plane. So 1, 0, 0 for one may be like this, for another it may be like this, third it may be like this, fourth it may be like this, fifth it may be like this. But 1, 1, 1 is always like this. If it is so, which is again an ideal case, if it will never happen that for all the crystals, 1, 1, 1 is in like direction, then you have perfectly oriented the film. Okay, I will call it a oriented film. But if it is not so, but somewhat preference, let's say a significantly larger number of grains are like this, and others are, still there are reasonable amount of grains for which 1, 1, 1 is not in this particular direction, we call it a texture. So texture and orientation are meaning same thing. As such, one is little more stronger word, orientation is little more stronger word than the texture. Okay. Now, many times you want to create these type of textures in order to shape your mesh loop. And how you texture them, it again depends on the way you make the material. In fact, even in the bulk, especially in this, even in the steels, I'm not a metallurgist, but I understand that people try to orient, what they call as a grain oriented. You try to create an orientation for obtaining certain amount of properties. Though I don't understand steel, let me admit it. All right. So this is what happens, and therefore texture and orientation also becomes a very, very important aspect for utility in a polycrystalline material. If you are having good fortune of working only on single crystal, of course you will have a difficulty to make them, but if you make them, then life is comparatively easy. But for polycrystalline materials, life is more difficult because this texture, which is an extrinsic factor, because for the same material with the same composition, you could have completely different mesh loops, depending upon how you have textured it and how you have oriented them. Okay, then your life is a little more difficult. One more thing I would like to mention before I go ahead to the next topic. Sorry. What happens when we try to make the size or the grain size very, very small? See, sometimes people also work on particles, which is not necessarily polycrystalline material. We just work on particles. You will see a lot of papers being published on particles. We just say powder. Okay, and then we talk of particle size. So there is a difference between particle size and grain size. And I've discussed with metallurgists or material scientists, and they say very clearly defined grain size. When we talk, it means polycrystalline material. When we say particle size, we mean that's a powder. So we are talking of the size of the powder. That's what is the standard understanding about the grain size and the powder size. What happens if we start making them small and small? One effect I have already discussed, that if the size goes below a certain limit, you will find that the material will only have a single domain. You will not be able to create multiple domain. And therefore, this will behave more like a material which is only single direction. And depending upon the size, if in fact as in the particulate media in the old recording tapes, what people were using was needle-shaped materials. And biggest technology was to make those needles. And they were very, very tiny needles. And because they were needles, so magnetization will always be like, because of the magnetostatic energy, magnetization will always like to point out in the length, along the length. You get a beautiful porosity in these films. Only because most of the technology is not only that. You have a tape, you have to put all these particles in such a fashion that all these lengths are along this particular direction. In fact, the technology is so important and rather difficult. I mean, those people who lived in that particular era would know that magnetic tapes that we had earlier, in fact, when I was doing my PhD, we were using magnetic tapes even for memory storage. The memories were awfully small. If you are looking from this particular, discussing with Professor Shenoy, 1 TB, 2 TB. Okay, and when I was doing my PhD, Delhi University computer had a total memory of 100 kilobyte. And when I went for my first postdoc to Caltech, and that computer had 1 megabyte memory. I know myself, 1 megabyte, what a huge memory. Okay, so we are used for kilobytes, and suddenly you see megabytes, and now these things are not called memories. These are Have you ever thought that if you take a disk and it has she has a 2 terabit disk, all right, what will be bit size? Try to calculate it. Extremely tiny number. Extremely tiny number. If you have to pack that many bits into that small area, how much area a bit will occupy? And for technical reasons, the grain size has to be smaller than bit size. Okay. I will give you an idea. These are sort of qualitative sort of discussions, not really quantitative, but just to give you a feel of that particular thing. And sometimes I feel that this qualitative discussions give you better insight. Suppose I am writing a bit, let's suppose this much. And if I have a grain size which is bigger than the bit size, okay, so this is my grain. I have to create a domain wall within this. And if my bit size is small, the domain wall size will be going to be very small. You have to work against the exchange energy. Okay? Normally, a bit is written over many grains of particle size. So within this particular bit, there will be multiple grains. And if grain sizes are larger, you cannot cut these grains like this. Okay? Some will go away outside this particular bit also. Some will become like this, some will become like this, some will become like this. Some will become like this, some will become like this. Eventually you have to cut through some of the grains, which essentially creates noise. Okay? You would rather have this grain size as small as possible, so that this coming out of the bit size becomes very small. Okay? If I have very, very fine grain structure, then if one of them comes out, it will be very tiny thing. So effectively the noise will be much lesser. That's why I'm interested in small size particles, small size grains. Because if I have to look for that application, I have to look at very, very small sizes. So one other fact I have just now told you, that if you have very small size, you should have single domain. That does not bother for this. But there's another thing which is very important, which we have not talked about it yet, is what we call super paramagnetism. Both magnetism and superconductivity are classified as cooperative phenomenon. A single atom of iron is not ferromagnetic. You require exchange to create ferromagnetism. For exchange, you require multiple atoms. It's a cooperation between multiple atoms that make a particular material ferromagnetic. If you make grain size too small, then thermal fluctuations become very, very important, and they will take a very important role, and this particular material will start behaving like a paramagnet. See, what is a paramagnet? We had individual atoms which are having magnetic moment, but they are decoupled with respect to each other. And when I apply magnetic field, this particular material can orient itself in the direction of magnetic field, classical language, without affecting the neighboring atoms. A similar phenomenon will happen to all these tiny, tiny particles which have a very large magnetic moment on themselves, because they don't contain one atom, but they contain a very large number of atoms, but still the size is very tiny. They behave like independent particle, but with a very large magnetic moment. So that's why it's called super paramagnetism. But it will not show any loop. It will behave like, see, in a normal paramagnet, you show M by H by straight line, M versus H. Okay, of course, this is only valid so long the field is not very large. If you really go to as high field as you want, if that facility was available to you, eventually it has to saturate, because you have to have a fixed number of magnetic moments only. But it so happens that for most of the time, the type of field that we are working, this M versus H relationship is a linear relationship. That's why we talk of susceptibility, etc., all those things in the case of paramagnetic material. In the case of superparamagnetic behavior, it will show you a behavior like this and it will saturate much easier, but will not show any loop. So all that we wanted to achieve through magnetism is lost. In fact, in and around 2000 year, most of the work in recording industry was to how to decrease the superparamagnetic limit. And that's how antiferromagnetism and many other things become very, very important. Somehow to have as small size of the grain as possible and still retaining its ferromagnetic character. You realize that experimental and technological problems are very difficult many times. You have to achieve that particular thing. Okay, I will talk about recording a little later, but this I thought I will just mention a little bit about the small size particles and the importance of small size particles. Okay, these days to generate nanoparticles or nanograins is very, very common. Okay, you can very easily have grain sizes of the order of nanometers, maybe tens of nanometers of that order, easily done. Okay, but then we have to look at all these properties. Okay, if you are looking at the utility of this particular material. All right. Now there is one more thing which I want to do before I wanted to go about the bulk materials. Is about the magnetization. I am handling at the moment somewhat independent topics. You would excuse me for that. Yeah, please.
So supermagnetism only happens when the grain size is like very small, or is there any other possibility that we can see supermagnetism, but
Superparamagnetism.
I mean, yeah, superparamagnetism other than this criteria? Like, is it possible?
Not that I know. Superparamagnetism generally is related to size, but how small size again depends on anisotropy, basic anisotropy of the material. There is a very well-known paper of Beans, which is Beans and something like that. If you are interested, if you send me a mail, I will send you the reference. And that's the classical paper of Beans, which talk about superparamagnetism and refers to that. And everyone, even till today, uses that particular paper. Okay, where he has calculated various limits of what are the typical sizes. Okay, depending on the type of anisotropy, etc. Basically, I mean, it can always happen that for a certain type of material, you can go to much smaller sizes and still retain magnetism. Magnetism, by magnetism, I mean ferromagnetism. Okay, for some other particles, even at a much bigger size, they will lose. That can happen. But I do not, at least I am not aware of any particular case in which superparamagnetism can be observed other than when particle size or grain size are small.
And also, like the magnitude of the moment or magnetization. So how much different it will be? Let's say a ferromagnet material and for supermagnetism.
You are talking of the susceptibility. You are talking of this particular shape.
Yeah.
See, the thing is that when you fit the susceptibility, there is always a term of mu effective, which tells you what is the magnetic moment of an atom. I think this probably must have been derived earlier. Okay. Otherwise, you look at any standard book of Kittel, etc. It's a very, very standard. The normal Brillouin function, the way you eventually calculate the susceptibility. All right. Now, what will happen in this case? This mu effective, which was actually the magnetic moment of that atom, is replaced by the magnetic moment of a grain, average magnetic moment of a grain. Depending upon what is the grain size, it could be 1000 times, okay, 100 times, or whatever it is. Any other question? Please feel free to ask questions. As I have mentioned, that doesn't mean that I can answer all the questions, but I'll make my. All right. So let me talk about magnetism, saturation magnetization. This probably will also answer some of the questions which were asked yesterday about the localization and the itinerant nature of the electrons or magnetic moments. See, as we know, or as we have discussed, when we apply a magnetic field, the magnetization gets saturated. Okay, now we can use this particular value of saturated magnetization at low temperature, essentially, ideally speaking, at 0 K, to calculate what is the magnetic moment of the system. Because effectively it means saturation would occur when all the magnetic moments are aligned along the direction of field. We have said that it should form a single domain. But still at a normal temperature, thermal effects will play a role, and some of the magnetic moments, some of the naughty quotes, okay, magnetic moment will be slightly away from the magnetic field. So you have to really go to the lower energy so as to remove the thermal effects. So ideally speaking, the MS at 0 Kelvin can be used to calculate what is the actual magnetic moment on the system. All right, and then you can verify with your theory, which is whether it's giving you the same result or not. In fact, I had given one tutorial problem on this particular thing, just to give you an idea about that thing. All right, now what happens? Let me just give you the expression. I am interested in calculating NB, is the total number of magnetic moments in Bohr magneton unit. This is the value of Bohr magneton, and this is the total number of atoms, or total number of formula unit to be called, if we are not talking of a single atom, but a compound. I use this particular, it's a very, very simple expression. You have this MS0, you calculate the total number of formula unit per unit volume, you can calculate by density, you can calculate by lattice constant, there are multiple ways by which you can calculate. This mu b standard, I have given you the expression yesterday, it's a standard expression. Okay, you can calculate what is the value of NB. It means your total formula, how much magnetic moment it contains. And we have talked about the theory of that particular thing, how these magnetic moments arise using orbital angular momentum, spin angular momentum, blah, blah, blah. And we can compare with them, experiment. All right. Now, let me first talk about metallic magnets. If we take the metallic magnets, 3D transition metals, three most important ferromagnetic materials are iron, cobalt, and nickel. Iron magnetization at 0 K, extrapolated, of course you can never reach 0 K. It's approximately 1740 Gauss. Sorry, I am going to use Gaussian system of units. Cobalt is 1400. These values could differ slightly from which textbook you look. So I cannot guarantee they are the latest value, but or for the purest sample, because it does not depend only on the measurement but also on the purity of the material. But it's just to give you an idea. If you calculate from this the average magnetic moment on iron, this turns out to be 2.22 Bohr magneton. Cobalt, it turns out to be 1.72 Bohr magneton. remember, this is going to give you a value of only mu z. I have talked about it earlier. It's not the magnetic moment mu effective, which is under root j into j plus 1 h cross. Because by applying magnetic field, I am not going to achieve that. I am only going to achieve only the z component. That thing should be kept in mind, because there is always confusion about this thing, because experimentalists talk without any limit, with full freedom. This is the magnetic moment, and everyone understands it. But then somebody says, oh, well, no, this is not the magnetic moment. Magnetic moment is under root j into j plus 1. Oh, yeah, you are right. But on the other end, this is what we meant. All right. Now, normally, for all the 3D transition metal, this should be an integer, this Bohr magneton. You can calculate, and I have forwarded the notes, probably they will be circulated to you. All right. Why you are getting this? This is because of the band nature, which we call, because the electrons in this side, this is itinerant. I am going to give you a table of isolated atom and in the band on the average. This I have taken, I think, from Lax and Button, very, very old textbook. But this has been one of my favorite textbooks, working on ferrites. But normally when my students join me first, or used to join me first, I used to ask them to read at least first few chapters of Lax and Button. Very well written book about, I'm not sure whether you are familiar with Benjamin Lax and K.J. Button. It's 1962 book, Microwave Ferrites and Ferrimagnetism. Some of the basic things have been written very, very wonderfully in this first 2-3 chapters, which give you an introduction of magnetic materials, very, very beautifully described in this book. So if I talk of an isolated atom, this is all by applying Hund's rule, this. 5 minus 1 will be the 4 Bohr magneton will be the magnetic moment. And if you take nickel, 1 more electron, this is what should have happened in an isolated atom if we applied Hund's rule. So what I should have got for iron would be 4 Bohr magneton. For cobalt, I should have got 3 Bohr magneton. Nickel, I should have got 2 Bohr magneton. Remember, these are mu z values. Again, let me remind you. All right. But what happens because of the band nature? The atoms are distributed across the solid, and then you can only talk of the total number of atoms. All right. And then average number of electrons per atom. That can be fractional. See, so I am talking of one particular atom. I cannot say it has 1.5 electron or 1.3 electron. It has to have either 1 or 2 electron. But if there are 100th thing, okay, depending upon how many of them are available, the average number of electrons on this could be fractional. All right. So if I take this particular thing in a metal, these numbers change. And there is a very famous curve called Slater-Pauling curve, which tells about these particular things. it can accommodate maximum 5 electrons per atom. Okay? Remember, in this particular case, 3D up band and 3D down band both will have vacancies. All right? When I come to cobalt, this band gets filled. The vacancy is applied only, see, language has changed now because we are talking about bands. Okay, there are vacancies only in this particular band. All right? So this becomes 5. This becomes 3.3, 0.35. I'm not sure how they have obtained these numbers, but whether there are some band structure calculations or how they have done, I'm not very sure. Nickel, again 5, 4.4, 0.3, 0.3, now generally terminology used by a lot of people who are working on metallic magnetism, which is somewhat confusing, but let me mention. There are certain material which we call as a strong ferromagnets, some materials which we call as weak ferromagnets. And by strong, if you ask any random person, any layman, he will say, oh, probably iron is the strongest magnet. But according to this is weak magnet, because if you have vacancies both in 3D up and 3D band, then we call it a weak magnet. A strong magnet means the splitting between spin up and spin down band has increased so much that the band, one of the band is completely filled. So according to this, because cobalt 3D up band is completely filled, so these are called strong ferromagnets. So this is a terminology which is often used and which is often confusing when people are working in the case of metallic, especially alloys. In fact, what you can do, you can actually start making an alloy of iron, cobalt, nickel, and you can have other transition metal and make an alloy. So long the atomic number difference is within 1, sometimes within 2, okay, you can assume that band structure does not change. And then you get this Slater-Pauling curve, which is something like this. Whereas as you increase the average number of electrons, the magnetic moment first rises, and your cobalt is somewhere here. I'm sorry, iron is somewhere here. Then immediately after that, one of the band gets filled. Then, because all the electrons have to go to the other band, and total magnetic moment is the difference between this and this. So the difference, because this going up, like in this particular case, the difference will go down, and therefore magnetic moment will drop off. So in fact, if I am just looking at iron, cobalt, nickel, I am just looking at the 3 different points. One is here, another is here, and third is somewhere here. But by making alloys, you can scan this particular curve, where you can change the average number of electrons different from 8, 9, 10 to between 8.5, 8.3, but just making alloys of these, provided there is no change in band structure. If you mix, let's say, manganese with nickel, the atomic number difference is very large. This is going to cause change in band structure, and then this particular thing will not work. The Slater-Pauling curve is assumed to work only when there is no basic change in the band structure. All right. Any questions so far? Because now I am going to start a slightly different topic. Sure, no questions? Either you have understood everything or you have understood nothing. Only binary possibility. Now let me talk of some bulk materials, some bulk magnetic materials, mainly from the point of view of their utility. So one of the oldest material, magnetic material which was known is lodestone. Probably you would have heard about it. It's nothing but ferric oxide, Fe3O4. Then after that, metallic ferromagnets, they were very much in vogue, like iron, cobalt, nickel. Somewhere around Second World War, it was realized that there are likely to be high frequency applications of magnetic materials, especially in communication. When you are trying to work on a radar, which was important in the Second World War to detect the planes, it requires microwaves, and you have to use certain materials, certain magnetic materials, which can work at that particular frequency. Now, metallic materials were considered useless for that because they are conducting materials, and at high frequency, they'll have so much of eddy current losses that you will not be able to get any signal out of them. All right? So people were looking for materials which are insulating materials, which are oxides basically. And that is the time when we developed or discovered, if you want to call it, the ferromagnetic materials. The first ferromagnetic materials were what we call as ferrites. Just as anecdote, there has always been controversy who was the first discoverer of ferrite. All the European guys were always taking that Snook from Phillips lab who discovered, and all the Japanese guys were telling that it was, what's the name? I forgot the name. He was from Tokyo Institute of Technology. The name will come. He's the discoverer, and there is a lot of confusion who was the discoverer. Recently, on the Facebook, the Toyota Institute of Technology have put that they have got a particular, what you call a brass plate from IEEE transition magnetics. Congratulations for the discovery of ferrites. So it means they have accepted that it was Professor Takai from Tokyo Institute of Technology that he has discovered ferrites. So it's just because there has been some confusion. European always thought that it was Snook who had discovered ferrites. Anyway, there are multiple type of ferrites which are possible. Basically, these are magnetic oxides, ferrimagnetic oxides. Traditionally, three are the most common. There are three type of ferrites which are most commonly used, but as I said, there are many more. But generally, most of the work has been done on three different types, and it's defined with respect to the crystal structure. One is what we call a spinel, the structure that I had discussed yesterday in detail. The second, these are MFE204. Then you have garnets. As if spinel structure was not complicated enough, garnet is still more complicated. Even Smith and Winch book does not talk about it. They just write garnet structure is very complicated, that's all. After that, they start talking about its sites. All right? This has a rare earth in it, Fe5O12. Then you have hexagonal ferrites, which are generally used for permanent magnetic applications. There is M type. One of the most common hexaferrite is barium hexaferrite. This is M type. There are various crystal structures possible here also. Now we talk a little bit about Néel model. I've been talking about Néel model. This is called Néel's two sublattice model. Néel was the person who actually gave the idea of ferrimagnetism. He got Nobel Prize for that thing. In France, there are two laboratories. I had the fortune of working in one of them. One laboratory was in Grenoble, another was in Bellevue. And all the experiments on ferrites were done by the Bellevue group. Professor Guillot was the one. Only thing he could not understand that he's getting magnetic movement, but why it's coming out so small. That was the only issue. So you have magnetic material, you know what is the magnetic moment of iron, you know what is the magnetic moment of cobalt or magnetic moment of nickel, okay, and you do only ferromagnetism. So you should expect some magnetism, magnetic moment, and you're not getting that, you're getting much smaller value. And using the same data, in fact, if you look at the Neil's original paper, he has referred to Guillau's work. He used Guillau's work to say that they're antiferromagnetically coupled, and because of that, the magnetic moment is turning out to be smaller, which brought him Nobel Prize. Guillaume did not get Nobel Prize, of course. All right. So what essentially Neil's model says that AB interaction is the strongest antiferromagnetic interaction, which we have discussed earlier last time. And when present, mind my language, when present, it will dominate over AA and AB exchanges. All right. So what is the exchange interaction between A and A and B and B? We will not care for it. Though that happens also to be antiferromagnetic, but he does not care about it. He says that this is so strong that all the magnetic moments in the A side will become parallel to each other, and all the magnetic moments on the B side will become parallel to each other, and magnetic moment of B will align antiferromagnetically with magnetic moment of A. Is it clear? That's what is Neil's model. Okay. So net magnetic moment, how do I calculate net magnetic moment? MS. Simple, you just do a loop, find out what is saturation magnetization, calculate what is the net magnetic moment, and see whether it works. Actually, I should have written modulus here, but normally for most of the ferrites, mu B is larger than mu A, so that's why I'm writing mu B minus mu A. This is what is Neil's model. We have discussed earlier normal ferrite and inverse ferrite, and how which magnetic ion will go to which site. There could also be partially inverse ferrites. It means they are not fully normal or fully inverse. So there in between possibilities also exist. If you want, I can give you the data, but these notes will be available to you. So I'm not writing in order to save time, because I'm already, I think I'm not missing time. Today is 11 o'clock, my lecture is ending. Okay. Now let us look at what are the various applications. Over the ages, ferrite is a very old topic, almost 70 to 80 years old. There has been a lot of work on this particular thing, lot of doping, and these ferrite materials were exploited to a large extent for various applications. I will list out a few applications here just to give you a feeling of how they have been useful and why people are still working on ferrites. That of course probably will come in the next lecture, but at least let me talk about the bulk ferrites. Here I am listing 4 major applications. There could be many more minor applications. It does not mean that these are the only applications. One is what we call a RF frequency application. Which essentially means up to 10 megahertz. Looking at the range of frequency over which ferrites can be utilized, this is the lowest frequency range. Of course, if you are talking 50 hertz, etc., now you are using metals. their eddy current losses are. I mean, if I want to use a transformer core, for a transformer core, I don't want to use a ferrite material, okay, because it's not going to give me that type of magnetization. See, magnetization, because they are ferrimagnetic, is much smaller than metallics. You understand? Iron has 22,000, MS is 1740. If you take 4 pi MS, it's 22,000. Huge magnetization. Okay. You are never going to get that in oxide because of the ferrimagnetic character. All right. So why not use which has a larger magnetization, and you are not bothered by 50 hertz. So you use all metallic materials. There also there have been some changes which I will discuss. All right. Now, in this case, resistivity is not that important to be high. It should be high. It cannot be as bad as metals. It has to be resistive, but we do not play a very important role on, we do not assign an important role on resistivity, but more on the magnetization values. I would rather like to have larger magnetization, even if the resistivity becomes slightly lower, I don't care. So there are ferrites like manganese zinc ferrite, nickel zinc ferrite. Which have been developed for these frequency ranges. They have generally one of the highest magnetization in normal ferrite systems. But they do not have a very, very high resistivity. All right? In fact, in many of these applications, you are looking only at the reversible part of your MS loop. You are looking only at this particular part. And therefore, initial permeability is very, very important in these materials, because you are looking for some applications where once you remove the field, you should get back 0. All right? And therefore, in fact, if you look at the various parts of the MS loop, I had talked about initial permeability or initial susceptibility rather. All right? So these are the materials where initial susceptibility is very high, making them useful for these type of frequency applications. Second is we go to the microwave frequencies, and when I go to microwave frequencies, resistivity becomes very important. Then you cannot afford a resistivity even though magnetization is lower. So for example, yttrium iron garnet has a very low 4 pi MS, something like 1700 or so, but it has a very good resistivity, very high resistivity. You would prefer to use that rather than using manganese ferrite, which has a much larger magnetization but also have a smaller resistivity. I am mentioning low power. Because for high power, there is a special requirement. It means in normal devices you are using. But high power means when you are using actually for radar application, you are pumping a huge amount of power. So microwave frequency, you use magnesium manganese ferrite, lithium zinc, also garnets. Of course, lot of work in this particular area is classified work, because most of the time for defense purposes, these are the very important type of materials. IIT Bombay has worked on many of the defense projects on this class of ferrites. We are looking at very high frequency applications. High frequency, not only high frequency, but high power applications. Here it's very important that, because high power, you are always going to heat the material. Okay. magnetic property should not change with heating. And also how the power is dissipated to the system, that becomes very, very important. So here the things that we are looking, not only high resistivity is very, very important here, but also there are many other things which we are not looking for low power applications, is essentially the heating effects. How essentially it changes the properties of the materials upon heating. So high power has a very, very different type of phenomena. People who are experts only in high power, they work only in high power applications of these materials. Here we are using again lithium zinc, of course with special dopings. Here exact compositions probably you will not know, because many times these are sort of classified. And most important are dysprosium and holmium based garnets. So the application of garnets are more towards microwave frequencies, because they have very good resistivity. Good, by good I mean very high resistivity, though much lower magnetization. The fourth is a permanent magnetic material application. We will be discussing about permanent magnetic materials a little bit later. But let us realize that ferrites are not the best permanent magnetic materials known. There are much better permanent magnetic materials known, but they are one of the cheapest. For things for which you do not require, very, very common application which probably consumes a very large number of these ferrite materials are fridge magnets. You have seen fridge magnets. Refrigerator people stick. You go to some place, there is a souvenir, there is a tiny magnet which you can stick to your fridge. They are all in this category, very cheap. If you want to use, you may get very good, permanent magnetic material property if you use samarium cobalt, but that will cost you a hell of a lot. Nobody will buy that souvenir. Ferrites are good enough. So they produce a very cheap type of, though not very good permanent magnets, but cheap permanent magnets, and it has its own market. See, remember, many times the research in the world is driven by economy and not by physics. All right, you may have wonderful physics behind it, but eventually, if somebody is going to fund your research, okay, he's going to fund only if he's going to make money out of it. And the industry is going to fund only that way, and that has many times biased some of the very good research work, and because they were never funded. To get money was not all that important. I think I'll stop here because I'm close to 11 o'clock. Because if I start another topic, it will take a little bit of time, and if you have any questions, I'll be very happy to answer. But I would be happy if you ask some question. See, one of the reasons people don't ask questions, that people feel that people will say, oh, how stupid question. No question is stupid question. In fact, most of the time, the most stupid question has led to the best solutions, best physics. So all questions are equally important. Always there is some doubt, something in the mind which you do not understand. Otherwise you could have gone to a recorded lecture and listened to it. When a teacher is present in front of you, better ask.
Okay, if there's no further comments, we'll break for tea.